歡迎大家嚟到我哋今日嘅呢個專題講座啊！咁我叫陳俊霖，係太空館嘅助理館長。咁啊，太空館其實大概每幾個月啦，都會安排一啲專題講座嘅。咁我哋更難得嘅咧係能夠安排到一啲外國嘅講者咧嚟同大家分享呢個專題講座。咁當然啦，我哋好多謝天文論壇啦，同埋謝順基金啦，同我哋一齊合作，咁可以邀請到外國嘅唔同講者咁嚟我哋呢度做講座。其實過去幾年咧一直都有嘅。咁嘅過去都好多知名嘅講者都嚟到呢度同大家演講，咁啊，所以都好多謝我哋香港嘅唔同天文愛好者，咁啊一齊努力啊，咁啊希望令到就更加多嘅機會喺太空館呢個場地咧，就可以舉辦到一啲嘅天文嘅講座。咁係啦，咁啊今日嘅講座咧就月球嘅365日啊，係太空館啦、我哋天文論壇啦，同埋謝順基金啦，咁一齊去合作舉辦嘅一個活動嚟嘅。咁我相信在座好多朋友都認識天文論壇啦，咁我自己細個都睇天文論壇睇大嘅，咁啊係一個嘅。如果我冇錯嘅話咧，應該係當年啦，我哋喺太空館咧就舉辦羅鏡班開始，咁啊成立咗論壇，咁啊希望羅鏡班嘅朋友咧就一直喺論壇呢個地方咧可以交流啊。咁但係後來發展得越嚟越好啦，就令到更加多本地嘅同好咧都繼續喺呢一個地方去交流好多一啲天文嘅經驗啊、一啲觀察嘅一啲技巧啊，甚至一啲活動嘅資訊嘅。咁而謝順基金咧係香港嘅一個慈善信託嚟嘅，咁啊致力推動華人社會嘅一啲藝術創作啦、保育同埋傳承工作。咁而家支持嘅項目咧，仲有一啲嘅傳統嘅珠寶手工藝嘅傳承、粵語流行曲嘅保育同埋推動呢個星空保育嘅天文攝影嘅。咁啊，今日嘅講座咧會用英語進行嘅，咁我都用英語簡單講少少個背景先。So today's lecture is jointly organized by the Hong Kong Space Museum and the Hong Kong Astro Forum with TSL Foundation as a program sponsor for the Hong Kong Astro Forum. Hong Kong Astro Forum is open mainly for the participants of telescope making course of the Space Museum to communicate with each other and share experiences in telescope making. So at the same time, it also provides a platform for different astronomy lovers in Hong Kong to share the experience in astronomical observations in the internet. And the TSL Jie Shui Lun Foundation is a charitable trust in Hong Kong and is committed to foster the works on creative arts, preservation, and inheritance of Chinese society. The current supported projects include the inheritance of traditional drawing craftsmanship, preservation of Cantonese popular music, and fostering the astrophotography for night sky observation. 咁我哋今日嘅講者 Robert Rees 咧，其實佢就有好耐嘅月球觀測經驗嘅，咁遠過我出世之前啦嚇。咁我嘅資料咧就見到1958年啦，我都想象唔到嘅距離啦，就已經開始咧做月球嘅探索㗎。咁喺1959年咧就開始拍攝呢個月球嘅照片。咁去到近來啦，自從呢個 Internet 即係 hit 咗之後啦，咁喺 Facebook 上面咧都做咗好多同月球相關嘅項目啊，咁令到佢哋一啲月球嘅 project 可以喺網絡上面咧更加多人認識嘅。咁亦都係一個好資深嘅天文攝影師啦，喺1984年以嚟咧發表咗好多嘅一啲天文嘅雜誌啦、文章啦，一共超過250篇嘅，都係關於天文學嘅一啲文章。咁佢喺數碼呢個月球攝影咧得到啲啟發啦，咁寫咗第5本書嘅，之前一直出版好多書啦。咁去到喺2019年咧就第5本書嘅，就係用中文咧就叫《與羅伯特里夫斯探索月球》。咁Robert 啦都經常喺我哋天文學界唔同嘅會議入邊咧發表啲演說嘅，咁提佢對月球嘅一啲熱愛啦，甚至咧小行星26591咧都係用佢嘅名去命名嘅。咁大部分時間咧就係Robert 咧就係喺美國嘅德克薩斯中部佢個人嘅一個天文台咧 Prospective Observatory 咧去進行觀測嘅。So Robert Rees has been exploring the moon since 1958 and took his first lunar photography in 1959. His Facebook project, 365 Days on the Moon, has repopularized the moon within the amateur astronomy community with over 40,000 daily readerships. Robert is also an accomplished deep sky astrophotographer and has published over 250 magazine articles and 170 newspaper columns about astronomy since 1984. His experience with digital lunar photography has inspired him to write his 5th book, Exploring the Moon with Robert Rees, to be published early in 2019. Robert enjoys speaking to astronomy conventions and spreading his passion for the moon. Astronaut 26591, Robert Rees, is named in his honor and he is now observing from his Prospective Observatory located in Central Texas in the United States. So 我唔詳細講太多嘢啦，咁我哋咧仲用今日嘅我哋用熱烈掌聲啦，歡迎我哋今日嘅講者 Robert Rees. Please give a big hand to welcome our speaker today, Mr. Robert Rees.
Is this thing turned on? Yes, it is. Well, thank you very much for having me here. This is a serious honor for me. This is really overwhelming. I've got a lot of people to thank for getting me here. And it all starts back in San Antonio, Texas, in my own backyard, where none of this would be possible if it wasn't for the support and love of my dear wife, Mary. All astronomers who are married need the support of their wives, or it's really tough to do astronomy late at night. And let's face it, astronomers are not like regular people. Very few people are going to go out in the middle of the night and do what they love. But that's normal for astronomers. And Mary has always supported me on that. And of course the TSL Foundation, Tommy C., he has brought me over here. I'm extraordinarily grateful for the experience and being able to meet fellow lunar observers, and especially K.C. Powell and Mr. Chu, who I've respected and admired for many years. K.C. is the one who steered me back toward the moon 15 years ago when he started posting pictures on the Internet Lunar Photo of the Day. And inspired by his images, I tried it myself, went back to the moon. I began with the moon 60 years ago, worked with Deep Sky, went back to the moon thanks to his inspiration, and here I am today. So it's kind of like coming home, back to the people who got me going on this. So let me get the lecture going here and tell you a little bit about myself. Well, I've been in love with the moon for my entire life. My earliest memories of the moon were watching moonrise through my bedroom window when I was a child. I still remember that, back in San Antonio, Texas. Early on I realized that at certain times of the year the moon rose through that window from when I saw it from my bed. Other times of the year it rose through that window. Something was changing in the sky and it got my interest. And I started exploring what makes the moon work. What is this strange world that I'm seeing outside of my bedroom? Today, space age explorations have not stripped the wonder and mystery I felt from the moon when I was young. The moon still holds the same passion for me as it did before we went to the moon, before our space program took us to the moon. And there's a name for people like me who really enjoy the moon and want to explore it. We're called selenophiles, a person who loves the moon. And if you're here in this audience tonight listening to me, you too are a selenophile, a person who loves the moon. A little bit of my background. In 2000, I published a book called Wide Field Astrophotography. It was well received, but at that point, film technology was fading out. Digital photography was coming on. And the whole way photography was done changed just about the same time I published this book. So in 2005, I published another book, Introduction to Digital Astrophotography. This was the first book written about digital astrophotography using a DSLR. So although I'm well known now for my lunar photography, I very much enjoy deep sky photography. I shoot through a teleview refractor with my DSLR camera, and I enjoy exploring the Milky Way. But in 2006, I published another book, Introduction to Webcam Astrophotography. Because of the inspirations of you, I turned to the moon and discovered what a fantastic tool this was. Just with a simple webcam, I was out shooting what all the professionals used to do with the big telescopes, the professional observatories, getting better detail on the moon from my own backyard with a simple telescope and an inexpensive little webcam than what the professional observatories were doing in support of the manned space program. So I like to think that that book, Introduction to Webcam Astrophotography, helped popularize the use of the webcam video capture for planetary photography and help launch the industry today. The QHY cameras, the ZWO cameras, the Celestron Skyris cameras. Those are all an outgrowth of hopefully my book popularizing this method of astrophotography. So my pictures have appeared on the covers of magazines, they've appeared in magazines, they've appeared on the covers of books, they've appeared in books as illustrations. One thing I'm particularly proud of is people buy my pictures, my big prints, and take them to astronaut autograph shows, and people who have actually walked on the moon sign my pictures for people. I wish I had one of those pictures with all the signatures on it, but it's an honor that astronauts who have walked on the moon sign photographs that I have taken. And who knows, some of you may be actually sitting on one of my moon pictures. If you have the cell phone cover by Spec that has a picture of the moon on it, that's my moon picture. So over the past 10 years, I spent a large amount of time chasing big telescopes all across the southern United States in an effort to take high-resolution lunar images. And when it all boils down to the end of the day, I find that I can take better pictures with a small telescope from my own backyard than I can chasing these big telescopes. And I use a 180 millimeter Maksudov, the two on top. I've got a Celestron 11 and my original Celestron 8 that I've had since 1975. And I can take better images with those because the smaller telescopes aren't degraded by the shaky atmosphere, the bad seeing. What the turbulent atmosphere will blur the image in a large telescope more than it will a small telescope. So there's a limit to how much a bigger telescope will help you. And if the air is shaky and bad turbulence, a big telescope will actually work against you. So there seems to be a break-even point in the 8 to 11 inch range where we can do really, really good work and outperform what the professionals used to do back in the old days. So how good is modern imaging, lunar imaging with a modest telescope? Well, the image on the right is a plate taken from the famous Kuiper Lunar Atlas prepared back in 1960, using the best photographs taken through the best professional telescopes. This atlas was prepared in preparation for the upcoming lunar exploration, the manned Apollo expedition, helped planning for sending men to the moon. The left-hand image was taken in my own backyard with a Celestron 11 telescope. So, an ordinary Skyros camera that you can buy from Celestron. So, I'll let you be the judge, which is the better picture. I think we amateurs have outperformed the professionals when it comes to Earth-based lunar photography. So I want to say that I have no special talent. I'm no different than anybody else, but I am passionately curious. And if you're here tonight, today, in this audience, you are too. You're curious about the world around you. You're curious about the universe above. So you're no different than me. You're a curious person who wants to learn, and if you follow your passion, you can do the same thing that we do. So, the moon is my playground, and I invite you to come out and play with me. So, when I was young, the moon is what we call in America a big deal, something important. The moon was a dream, a goal, it was a destination, a place of mystery to be explored by brave astronauts who dared to venture to another world. In the mid-1970s, however, there was a fundamental change in how amateur astronomy was done in the United States. The introduction of the lightweight, portable 8-inch Schmidt-Cassegrain telescope gave us an affordable, portable telescope, easily transportable, and allowed us to get out of the city, get into the dark sky, and start exploring deep sky. The moon then faded from the amateur astronomy scene. And that's kind of sad, because the moon is what got a lot of us interested in astronomy to begin with. So the goal of my presentation is twofold. to bring the moon back within our astronomical realm, to make it something not to be avoided because it interferes with the deep sky, but something to be enjoyed from our own backyard easily every night. And I want you not to just to look at the moon, but I want you to understand it when you see the moon through a telescope. Whoops, too fast. So today we're going to look at a number of things: the creation of the moon, the evolution of the moon's face, the status of the modern moon, how we understand it, and to explore the moon through a telescope. So the creation of the moon, 4.6 billion years ago, before there was any life on Earth, before there were oceans, before there were anything. The moon was created by a huge collision between two worlds, our own proto-Earth and a planet that we hypothetically call Theia. These two planets circled the sun in a similar orbit, and eventually they collided. And in the huge collision, the shattered remains of both planets recoalesced into the Earth, and portions of it were slung out into space and coalesced into the moon. The early moon was hot, molten. In this molten moon, the heavy radioactive elements sank to the middle. The iron sank to the middle. The silicates and light elements floated to the top. In a global magma ocean, the entire surface of the moon was molten. And it took literally millions of years for it to cool down into a solid object. And when it did, formed into a solid object, a cooler surface world, its face began to evolve. Before, almost 4 billion years ago, we call it the pre-Nectarian epoch, it was the formation of the moon as a solid physical world. And then between 3.85 and about 3.92 billion years ago, we encountered what we call the Nectarian epoch, where the moon's face was formed by thousands of asteroid impacts. There was a period of about 100 million years where all of the inner planets were showered by massive meteor and asteroid impacts, and it's what created the face of the moon that we see today. That was followed by the Imbrium epoch, lasted almost 1 billion years. At that point, lava eruptions flooded the near side of the moon and created the dark regions we see now as the lunar maria. It's what created the face of the man in the moon. That was followed by almost 2 billion more years where additional cratering pockmarked the moon and created all the familiar craters we see today. The modern era, the Copernican epoch, began about 1 billion years ago, and the moon has been fairly static ever since. The only changes were the creation of the big crater Copernicus and Tycho. The moon has been fairly static for the past 1 billion years. The early moon didn't look at all like what we see today. After the late heavy bombardment during the Nectarian epoch, there were no lunar maria, no dark seas on the moon that created the face of the man in the moon we see. The moon was covered with giant craters. The largest of them we call basins. And these basins eventually flooded with lava to form the modern face of the moon. And then that was followed by even more cratering, which kind of decorated the face of the moon and made it what we see today. So the evolution of the moon has taken millions of years. Very explosive formation at first, coalesced into a solid ball, massive bombardment, altering its face, volcanism, changing the face of the moon. Now, the most important thing we need to understand about how the face of the moon was created is the idea that it was done by massive impacts, giant asteroids crashing into the moon. These impacts created the basins on the moon, and people don't quite understand the concept of a basin on the moon. The basin is nothing more than a very big, big crater. If the crater is more than 300 kilometers wide, we call it a basin. and the dynamics of how these basins are created. When the asteroid smacks into the moon, the impact is so forceful that solid rock reacts almost like a fluid. There's ripples because of the impact. The impact rebounds and creates ripples that go out in waves, and each ripple goes out and freezes into a raised rim. So we will see the effects of that shortly, how this is so significant in understanding the geology of the moon. These giant basin impacts define what we see today on the moon. The Procellarum Basin, the most massive impact on the moon, occurred about 4 billion years ago. It created a crater that was literally almost the size of the face of the moon. And then that crater itself, the Procellarum Basin, was overlaid by the Imbrium Basin, which created another giant crater on the moon. And the effects of that can be seen today. We can trace out the geology and the evolution of the face of the moon because of the effects of these ancient impacts. When we look at the moon through a telescope, everything we see on the moon was created by just two forces: impact cratering or volcanism. The Mare, the dark regions that form the face of the moon, these are all lava fields that were created by massive volcanic eruptions almost 3 billion years ago. The highlands, the bright areas of the moon that aren't dark, these are the original crust of the moon that wasn't flooded by volcanism. So giant meteor impacts and volcanism is the only thing that forms the face of the moon, or creates the features. We'll explore a lot of other features here shortly, but each one of them was formed either by impact or subsequent volcanic modification. That's the only thing that created the face on the moon. And of course, there's the fact that the moon is incredibly far away. This is the Earth and the moon in scale. And it had to be a very brave person to get on a rocket ship and travel from our lovely blue Earth all the way over to this small little world so far away. So, let's go through a summary of our understanding of the physical moon. We've studied the moon through a telescope for almost 400 years now. And there are some things that we understand and some things that we don't. But what we do understand is the moon is not the primordial object we thought it was before the space age. Back when I first started studying the moon, we thought the moon was like a time capsule, a piece of the early solar system that had been unaltered over billions of years. Well, it's not so. The moon is made of rocky material that has been melted and heavily modified by both what we call exogenic and endogenic forces. Exogenic force is something that affects it from without, from the outside. Endogenic force is something that affects it from the inside. The outside force, of course, is the impact, meteors. The endogenic force is volcanism, lava coming up from below. Now, two conclusions were drawn about the moon before the space age, before we ever sent spaceships to the moon, before men traveled there. The moon underwent a huge bombardment, meteor bombardment, about 500 million years after it was formed. That's what we call the late heavy bombardment during the Nectarian epoch. Then, for another almost billion years, volcanic activity began and formed what was the current face of the moon. After 50 years of intense research, we know the moon is lifeless. We cannot find any living organisms, no fossils, no organic compounds on the moon. Life never started on the moon. Now, the lunar evolution process through the accretion of smaller bodies and then melting because of impacts have left the moon with a crust about 60 kilometers deep and a uniform lithosphere reaching about 1,000 kilometers below the surface of the moon. There's a partially liquid core at the center of the moon. but we still don't know if there's an iron core at the center of the moon. It's one of the mysteries we haven't completely solved. Now, the oldest rocks on the moon are the 4.6 billion years old light-colored highlands, the areas that aren't covered with the dark marl. The highlands are rough, cratered, mountainous. The youngest rocks on the moon are the 3.2 billion year old maria, formed during the volcanic eruptions. Therefore, the youngest rocks on the moon are as old as the oldest rocks on the Earth. The Earth and the moon formed from the same source material. That is, that big giant impact 4.6 billion years ago, when the proto-Earth was struck by Theia, and both worlds were shattered and reformed themselves. The Earth and the moon formed similarly, but the moon is depleted in iron and volatile elements. The heat of the impact, the enormous heat, vaporized all the volatile elements on the moon. Those were kept by the Earth. Lunar rocks formed in high temperature events with little chemical reaction with water. There's very little water on the moon. Earthly geology relies very heavily on water, but the moon formed without water. And the evidence of the earliest events that formed both the Earth and the moon are now seen only on the moon. Our weather, our plate tectonics, our oceans have erased all of the early geologic evidence of how the Earth was formed. But on the moon, it's preserved. We can look through our telescopes and see with our own eyes the way the moon was billions of years ago. You can't do that with Earth. So, lunar rocks can be broadly categorized into three different types. There's the volcanic basalts that erupted from the interior of the moon and formed the maria, the dark areas on the moon. There's something we call northosites, which are the lightweight material that floated to the surface of a molten moon early on and then solidified billions of years ago. And then there's a third kind of rock called a breccia, which is created by the mixing of other lunar rocks by being crushed by meteorite impacts. So after the molten moon solidified, it was blasted by thousands of asteroid impacts during the late heavy bombardment. Now, the largest impacts created the large basins that we see flooded with lava to form the maria. And the primordial moon was much closer to the Earth than it is now. It's one thing a lot of people don't realize. When the moon was created, it was no further away from the Earth than the communication satellites we have in orbit, up at 22,000 miles. The moon was that close. So you can imagine that if there was an earthly ocean back then, tides were hundreds of feet high and would wash hundreds of miles inland. It was a very chaotic, very rough world back then. Now, the curious thing is the crust on the far side of the moon is thicker than the near side. And that has a very important effect. Most of the volcanic flooding of the basins occurred on the thinner near side. There's very little dark maria on the backside. The dark ridges that create the face of the man on the moon are concentrated on the side that faces us, because it could erupt through the thinner crust, while the thicker far side blocked volcanic eruptions. There's very little volcanic activity on the backside of the moon. And the higher density basalt that lies in the near side basins, the dark regions that form the face of the moon, they displace the moon's center of gravity just a little bit and locked that face toward us, so that the near side of the moon is permanently facing us. It's in synchronous rotation. The moon rotates once around its axis every orbit, so it keeps the same face toward us continuously. And over the billions of years of its existence, the moon has been blasted by countless meteorite impacts that has crushed the upper layer of the crust into a mixture of dust and rock fragments we call regolith. The surface of the moon is not solid rock. It's a very dusty, stony material that is very much like strolling on a rocky beach with beach sand and stone mixed together. And because these meteorite impacts excavate rock samples from deep within the moon's crust, it's possible to analyze the interior of the moon by samples returned by spacecraft and the astronauts. So, now that we understand a little bit about the physical moon, we'll explore the moon through a telescope and get an understanding of the face of the moon. What makes it tick? What created these features we see through a telescope? We're going to look at the Maria, the dark regions, the mountains, see how they were created, look at the different types of craters. Lunar craters aren't just holes in the ground. There's different kinds of craters. They have personalities because there's so many different types. We're going to look at rills, which are the grooves and channels carved into the moon, scarps, the cliffs on the moon, volcanic features. And then finally we'll wrap it up by looking at some sentimental favorites, some favorite views through a telescope. And I need to point out all the pictures that we're looking at were taken by me through my telescope in my own backyard back in Texas. And before we jump up there, one of the popular questions I'm asked is, can we see where the spaceships landed on the moon? Can we see the lunar landers? And sadly, even with the best telescopes, we can't see something that small on the moon. The lunar landers, even the shadows cast by the lunar landers at sunrise, are no more than about 50 meters long. But through the best telescope, under the best conditions, we generally can't see features smaller than about a half a kilometer. So sadly, the only way we can see proof that Apollo landed there, or actually there's photographs of the Chang'e 3 on the near side of the moon too, the Chinese lander. The only way we can see that is spacecraft photos taken from lunar orbit with a lunar reconnaissance orbiter. And the State University of Arizona has a marvelous website where you can see all of these pictures and actually see the footprints of the Apollo astronauts as they walked around the landing sites. Humans made those footprints. We were there. People who denied the moon landing, I'm sorry, it's right here in black and white. You can see it yourself. So, Apollo 11 landed right about here in southern Mare Tranquillitatis back in July 20th, 1969. I remember that day well. I was living in Virginia in the United States, and I was able to see the whole thing. And then China joined us. Touchdown right here in Mare Imbrium back in December 13th, 2013. So they've been up there for 6 years. And now, just this week, since I've come over here to Hong Kong, the Israelis have launched a spaceship to the moon. It's on its way. So the moon's going to be a crowded place. It's not just the United States, the old Soviet Union, China. There's going to be a lot of activity up there. Anybody with the will and the finances to do it can get to the moon now. So, let's start exploring the Maria. These are the dark lunar seas, the fields of dark basalt that are deposited by ancient volcanism. The basins on the moon and the Maria lying within them are not the same features. A lot of people confuse them and think that they're the same thing. But the basins were created by asteroid impacts, created these giant craters on the moon. The Maria were formed by lava eruptions that flooded the basins. Two separate events. And there's not all basins on the moon will contain a Maria. There's about 50 large basins on the moon, but there's only about a dozen of them that are filled with basalt to create the Maria. And the Maria define the face of the moon and create the caricature of the man on the moon. And there's 21 named Maria on the near side of the moon. 11 were named by Giovanni Riccioli in the 17th century when he first mapped the moon. And 8 were named in the 19th and 20th century. And then 2 more were named in the space age, since we started sending spaceships to the moon. Mare Nectaris. down in the southeastern corner of the moon. You can clearly see it's cradled in a round, giant basin, a crater. And it's kind of strange that it took almost 300 years to realize that. The reason astronomers didn't recognize that the lunar seas lay within giant craters is there was no similar feature on the Earth to compare it to. They had no idea such things could exist. They had no idea that asteroids could strike planets and alter them on such a global scale. But it was almost up to 1960 before this was accepted. In fact, there are some respected lunar scientists that even after the Apollo astronauts landed on the moon, still firmly believe that craters on the moon were created by volcanism instead of impacts. So it's been a long, slow process to really understand our own natural satellite. Some of it occurred, much of it has occurred within our lifetimes. Mare Crisium, it's really easy to see that this is laying in a giant impact crater. And yet, it took over 300 years for that concept to sink in. Again, no giant impacts were recognized on the Earth, so we don't have anything to compare it to. Mare Serenitatis, Sea of Serenity. It almost looks like a giant egg. But again, a giant crater that's filled in with volcanic flow. This is the middle of Mare Serenitatis, the Sea of Serenity. And it certainly lives up to its name as the Sea of Serenity because it's one of the calmest areas on the moon. The largest impact on this whole huge mare is 17-kilometer Bessel. It's a fairly bland, smooth, serene area on the moon. And Mare Tranquillitatis. It looks a little strange. It looks almost figure 8 shaped. It's entirely possible that the Sea of Serenity, where Apollo 11 landed, is actually laying within 2 basins. So it's not just one circular basin, but 2 of them together, which makes kind of a figure 8 shape. And of course, Mare Imbrium is very circular, very round, surrounded by massive mountains all the way around, and then over on the western side it blends into Oceanus Procellarum. It took a geologist to figure out what was really happening on the moon. Believe it or not, it was in the 1880s when Grove Carl Gilbert, an American geologist, realized that the face of the moon was created by impacts. But the paper that he wrote about it was very obscure. Nobody knew about it. It wasn't until the 1950s that his ideas were widely accepted. And we come to realize that all these features on the moon were created by giant impacts. Mare Humorum, down in the southwestern corner of the moon. Again, very obviously a giant crater that filled in with lava. It's so simple to see nowadays, but back in the old days, we just didn't quite understand. Of course, not all Mare obviously lay within a basin. The Procellarum Basin is so huge that it's been overlaid by later basins, modified itself. And Oceanus Procellarum, that lies within it, is the largest mare on the moon, but it's off to the edge of the moon, the western side of the moon, so it's not quite as obvious. It doesn't look as big as it is. It's actually twice as big as the next largest mare on the moon, but because it's so foreshortened off to the edge of the moon, it doesn't look as impressive as it is. Then there's places like Mare Australe, down on the southeastern edge of the moon. Doesn't look like a normal mare. It's not completely flooded with basalt. And the reason for that is it's near the edge of the moon, closer to the far side of the moon that has that thicker crust I was talking about earlier. So volcanism had a harder time pushing through that thick crust. And as a result, Australe is just a collection of lava-flooded craters instead of an entire basin paved over, smooth. And then finally, not all mare lie within a single basin. We've got Mare Frigoris, very thin river-like strip going across the face of the moon. It's the widest lunar mare, 18,000 kilometers, 1,800 kilometers wide, but only 200 kilometers high. It actually lies in a portion of several basins. Now, like I said, some were not named until, some mare are not named until the space age. Mare Cognitum, for instance, was partitioned out of Oceanus Procellarum in 1964 and designated as a separate mare. So lunar mountains, they're made differently than earthly mountains. Earthly mountains are created by plate tectonics, where the plates on the earth crash together and buckle up and form mountains, or they built up by volcanism. They were slowly eroded away by Earth's oceans and our weather. So mountains are continuously being formed, continuously being altered, continuously being destroyed here on Earth. The lunar mountains were created by a different process. Impacts. Remember I said the giant asteroids struck the moon and it made that ripple effect as the lunar surface rebounded, and each rebound would create a rim, a separate rim, a ring. Here we see the edge of Mare Imbrium is surrounded by the outer impact ring, the outer edge, the upturned rim of the giant crater, the Imbrium Basin. So we end up with linear mountain chains on the moon that were caused by an impact, not by volcanism or plate tectonics as on Earth. Up at the north of Mare Imbrium, we've got the Alps Mountains and Plateau Crater, very popular destination for lunar explorers with a telescope. The Alpine Valley cuts through it. And the Alps Mountains extend south and continue around and extend as the Caucasus Mountains on eastern Mare Imbrium, down in the southeastern part of Mare Imbrium. They continue as the Apennine Mountains, and then you get down to the southern part of Mare Imbrium, and the rim is formed by the Carpathian Mountains. So all of these mountain chains on the moon created literally 4 billion years ago, and they've stood since. Mountains on Earth have been created and destroyed a dozen times in that period of time. So everything we see on the moon is truly ancient, from literally billions of years ago. An interesting mountain range on the moon, we see the shadows here highlighting the Cordillera Mountains. These are very hard to see from Earth because a day earlier than this picture was taken, the shadow part of the moon was over here, and the Cordilleras were in the shadow. You can't see them. A day later, after this picture was taken, it will be full moon, and these shadows will disappear, and you can't see the evidence of where the Cordilleras are. So it's a very elusive lunar target that we'd like to track down at a very specific time of the month, just to be able to see this marvelous mountain range, because you need that shadow that occurs only on one day to be able to see them. And then other mountain ranges like the Juras, you can clearly see the rim of a giant crater that filled in with lava. Some prominent mountain chains, such as the western Crisian Basin, they remain unnamed. Not every feature on the moon is named. There's gaps. And I know Charles Wood, who ran the Lunar Photo of the Day that I mentioned earlier, the internet website. He is head of the Lunar Nomenclature Committee with the International Astronomical Union. Chuck Wood is the person in charge of naming the moon. And I've been bugging him a lot about filling in these gaps, but it's a tough process. There's a lot of features on the moon that deserve a name. So let's look at different types of craters on the moon. To understand craters, we have to understand the different kinds of craters. If a crater is less than 16 to 21 kilometers in diameter, we call it a simple crater because it's going to be a bowl-shaped crater, just a simple carving, dish-shaped excavation. But if it exceeds 16 to 21 kilometers in diameter, the dynamics of the impact do different things. First, the crater is going to have a central peak because the splash, the rebound of the impact, is going to bounce back up and freeze in a mountain peak. Plus, the outer rim, the walls, are so large that they can't support themselves. They collapse and tumble down toward the middle of the crater and form a series of stair steps, terraces. And then, of course, if the crater is larger than 300 kilometers, we call it a basin. And it's no longer just a crater. So, simple crater, like Helicon Leverrier, simple dish-shaped, bowl-shaped craters. Complex craters have the central peak and the terraced walls that collapse. And then, of course, a basin is larger than 300 kilometers, and it's no longer considered a crater. It's a basin. And here we see examples of prominent complex craters, all of them featuring a central peak, and you can see the walls collapse inward and tumble down in a series of terraces, stair steps. And crater rays tell us something about the moon as well, about the age of the crater. Crater rays will vanish after about 1 million years. They erode away by meteorite impacts, or solar radiation will alter the appearance of the crater ray. So after about 1 billion years, this bright splash of rays will vanish. So if a crater doesn't have any rays, a large crater doesn't have any rays, it's older than 1 billion years. If it does have rays, we know it's one of the younger craters on the moon. And then there's the giant ray system surrounding Tycho crater down on the southern part of the moon. A bit of a mystery with Tycho crater. We know that the rays that splash out from the moon were thrown out of the crater by the impact that created the crater. So if something struck the moon and created this impact crater, you would expect all the rays would radiate out from the center where the impact occurred. But look at these crater rays here that are not, they don't line up with the center of Tycho. They're parallel and tangential to the wall. And here's this rogue ray down here that doesn't line up at all either. It completely misses Tycho. So we don't understand what happened there. Why are these rogue rays not lined up with Tycho? And there's other kinds of rays. We call them butterfly rays, butterfly patterns. The ray pattern doesn't extend in all directions. There's this blank area. Or in the case of Messier and Messier A, they're all in one direction. What happens there is if a impact occurs at an extremely oblique angle, very shallow angle, it doesn't splatter the rays in all directions. There's a zone of exclusion in the direction that the meteor came from. If it's a very shallow impact, less than 5 degrees, and it strikes and creates the crater, the ray structure is going to be thrown out to the sides or downstream. None of it goes in the direction the impactor came from. So you can get an idea of how the crater was created, what direction the meteor came from, and how shallow it was. It creates this unique butterfly ray pattern. There's another class of craters called secondary craters. They're created by the material thrown out by an impact that creates a large crater. All that stuff, the rocks fly out into the air, they got to crash back down. They will create hundreds and hundreds of smaller craters around the primary impact. Big meteor came, crashed, created the Copernicus crater, threw out boulders, mountain-sized blocks of material, crashed back down on the moon and created all these secondary craters. Secondary craters are much shallower. they don't penetrate as deeply because anything thrown out from a crater cannot, it falls back onto the moon. It can't be any faster than 2.4 kilometers per second, because if it was exceed that, it will leave the moon entirely. It will escape into space. So all secondary craters on the moon are fairly low-speed impacts. Primary craters impact at about 20 kilometers per second or faster. So they're create a distinctly different kind of crater, much deeper crater. And not all craters are round. We've got these strange shaped craters like Haensel is peanut shaped, but it's actually composed of several multiple impacts. A normal round crater that merged together. Rheita E is several merged craters as well. However, Schiele is almost 3 times wider than it is long. That is not a perspective or slant perspective. It actually is cigar-shaped. And exactly what created that, we're not sure. We're assuming it was a very shallow impact, very large asteroid plowed out the moon and created this unusual elongated crater. And again, not all craters are round. We've got Anaximander up in the north, distinctly heart-shaped, very Valentine in shape. And of course, a little bit of lunar good luck. We've got this 4-leaf clover-shaped crater, Meton, up in the north. And of course, here we've got bullet-shaped Agrippa, bell-shaped Godin. Not all craters are round. You get all kinds of crazy shapes. There's even square craters, hexagonal-shaped craters. Another class of craters that I find fascinating are called four-fractured craters. These started their lives as normal, complex craters with, the bowl shape, the central peak in the middle, the collapsed terraced walls. But volcanism forced up from underneath the crater and flooded the interior of it with lava. Say Gassendi, Posidonius. We've got Posidonius here, but also a Hercules crater up here. As this lava forced its way up, it pushed the floor of the crater up. It was no longer dish-shaped like a normal crater, but it bulged up, and as the floor raised up, it cracked and split open. So it created this effect we call an oatmeal cookie effect. It looks like cookies your grandmother used to bake. Another class of craters is called ghost craters. These are ancient craters that were formed billions of years ago before the moon flooded with lava. And when the Mare formed and completely smoothed over the surface, some craters were already there, pre-existing craters. And we see them only by the very rim of them protruding above the field of lava. There's a very large normal crater, like Flamsteed P here. Used to be a complex crater, central peak, collapsed terrace walls, just like the others we've been looking at. But the lava flooding completely obliterated it, except for the very crown of its rim. Same with Stadius here. All these other little modeled craters here are secondary craters from Copernicus, like we were looking at before. And there's an interesting feature we call catena, which are crater chains, all related, formed at the same time. A string of craters, or a string of pearls, Catena Davy, Catena Abulfeda, all of these craters in a row were all formed at the same time. Same with Catena Mueller. Do any of you remember back in the 1990s when the comet hit Jupiter, Shoemaker Levy 9? How that comet broke up as it approached Jupiter. The gravity of Jupiter broke it up into multiple fragments, and each one crashed down on Jupiter in a row. Well, that's what happened here in the early solar system. Comets got too close to the Earth, and the gravitational pull of the Earth and the Moon broke them up, and the chunks of the comet rained down and smacked the Moon in sequence. Boom, 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 boom. and created these crater chains. Wrinkle ridges are another feature. We call them dorsum or dorsa by a scientific name, but they're wrinkle ridges. They're caused by folds in the Mare surface where various lava fields crush together and fold up a ridge. And these ridges, they don't exceed more than several hundred meters high. So we only see them when the sun is very low, sunrise or sunset, and they cast a shadow. At full moon, they almost disappear. They have no shadows, you can't see them. But they're rarely more than a few kilometers wide, but they can extend for hundreds of kilometers. Most popular one is, we call it the Serpentine Ridge, Mare Serenitatis. It's actually two ridges together. We call them Dorso Smirnov and Dorso Lister. And they form this ropey, twisted chain going along the eastern shore of Mare Serenitatis. All of these wrinkle ridges, not all of them, but they're named after Earth scientists. And they occur on almost all of the Mare. Not all of them are named, but we will take a look. Like Dorsum Hain lies on the eastern shore of Mare Imbrium. And that's this one arcing around here. And then up here, the Sinus Iridum, these unnamed wrinkle ridges, they look like ocean waves washing into a bay. And not all of these ridges are named. Mare Humorum has the series of wrinkle ridges across the center. And again, it's a feature that's not yet named on the moon. Lots of features on the moon, just begging for a name. Rills, big giant cracks in the moon, we can see these easily in our telescopes. And they're formed by 3 different processes. They look similar, but there's different ways that are created on the moon. Straight rills, like the Sirsalis rill or Rima Hesiotis here, if they're very straight, linear rills, they're caused by volcanism, a volcanic dike, which is a sheet of magma that pushed up from the core of the moon, pushed up through the crust, and split the crust open. But this volcanic dike, this sheet of magma coming up, never breached the surface, so it didn't erupt. It just reached far enough up where it split the surface, and where it spread apart, the land collapsed in between it. So it's a collapse of land between 2 faults, 2 geologic faults. It almost looks like a highway cut where somebody has excavated the land to build a highway. But these can extend for several hundred kilometers on the moon, and they're all formed by volcanism, volcanic activity. Another type of rill is called an arcuate or a curved rill. And this forms when lava fills the center of the basin, and as the lava gets deeper and deeper, the middle of the basin, it gets heavy and it crushes down the center of the basin, and all the lava starts slumping toward the middle. And as it pushes toward the middle, it stretches the land on the edge and pulls it apart and creates these big giant cracks, each several kilometers across. And then there's a third kind of rill called a sinuous rill. It was actually formed by flowing lava. Much like how flowing water on Earth will erode a stream and leave a riverbed, flowing lava on the moon will carve a channel. And we see them as these sinuous, almost snake-like rills crossing near the edges of the Mare. And then finally, a type of feature we call a scientific name is rupus, but we don't call it that. That's too technical. It's just a plain old scarp, a cliff. There's a lot of these on the moon, and they're the rims of ancient impact basins. This particular one, Rupus Altai, the Altai scarp, is the outer impact ring around the Nectaris basin, the surviving portion of it. The rest of it has been obliterated by impacts over the past billions of years, but this particular section of it has been very well preserved, and you can easily see it from Earth. Rupus Cauchy, same thing. A scarp, a cliff, but in this case, instead of being the outer part of an impact ring, it was created much like those linear reels we talked about earlier, where volcanic action pushed up from the center of the moon, split the land, part of it would collapse down and create a cliff. So it's a fault line where the land has collapsed because of volcanic activity. The most beloved of the scarps on the moon is Straight Wall, almost a little over 100 kilometers long. Here we see it as a dark line feature because it's sunrise. The sun's coming from this direction. The cliff is casting a shadow. It's only about 400 meters high, but because it throws that shadow, we easily see it from Earth. And one of the most easily recognized volcanic reels on the moon is Schroeder's Valley. Carved by flowing lava erupted out of the volcanic vent we call Cobra Head right here. And flowing lava flowed through here 3 billion years ago and just carved it out like a mountain stream, like flowing water on Earth. This is what I call the heart of the moon. See the heart-shaped area, the dark area? It's a hilly region north of the Aridaeus Rim, and, or the Hyginus Rim. And all of this is volcanic ash that blew out from a volcanic vent in the middle of this rim. And it dusted this entire region and gave it a darker shade. I call this region the heart of the moon. It's a name I gave it. It's not an official name, but I think it fits. It's right in the center of the moon. It's heart-shaped, and it's really easy to see in a telescope. And it's dusted down with dark volcanic ash. So it makes that mountainous region darker than the normal lighter colored mountains on the moon. And if you look down in some craters like Alphonsus near the center of the moon, you see the dark volcanic ash deposits around some of the volcanic vents within the crater. So volcanism is evident all across the face of the moon if you know what to look for. The Marius Hills on eastern Oceanus Procellarum, dozens and dozens of little bumps that are evident at sunrise, each one casting a shadow. Each one of those is a tiny little volcano, built up a small shield volcano, no more than about 10 kilometers across. Or up on northern Procellarum, Mons Rumker, this lumpy looking thing. It almost looks like a wad of chewing gum stuck to a sidewalk. It's actually a collection of volcanic domes, each one a tiny volcano in its own right. So let me wrap up the presentation today by just slowly scrolling through a series of just telescopic views, favorite areas, what I call sentimental favorites on the moon. So Plato and the Alpine Valley, that becomes a sentimental favorite for anybody who first starts observing the moon. Plato is so different. Got that dark floor on it, not a normal crater at all. And, no central peak, no rays, just this stark, dark Tycho crater down in the south. Very distinctive because it has the ray pattern during full moon, but right after sunrise we don't see the rays, but we look real close and we can see hundreds and hundreds of thousands of little secondary craters. You see each individual little spot, each tiny little crater is material blasted out of Tycho was showered back down across the face of the moon. Aristarchus Plateau, another volcanic region. Oceanus Procellarum, very flat and smooth. But we've got this 200-kilometer plateau that is built up volcanic, pushed up with volcanic activity. And Hercules and Atlas craters, Endymion crater, and broad Well, you can tell I'm a little tired. I know the name of that. Mare Humboldtiana, yeah. I'm still 14 hours behind Texas time, so I'm a little sleepy. Copernicus crater, one of the most favored on the moon because a massive race structure scattered in all directions. Back in the old days, back in the 1600s when they first started charting the moon with a telescope, we call this the monarch of the moon. And we follow the shadow on the moon, between the area between light and dark. We call it the terminator. That's where the detail is most easily seen, where the deep shadows reveal the depth of the moon, the craters. And here's Straight Wall again. And we see Straight Wall lies actually within a large unnamed crater. Except many large features on the moon are still unnamed. And here's more of those rills. The linear rills were sort of created by volcanism. Hyginus rill. Here's by Heart of the Moon again. Here's that ghost crater we were looking at earlier, Lamont. Looks like a big giant spider. Got wrinkle ridges radiating out from it. And a view along the southern edge of the moon. Away from the dark areas where the Mare is, there's this crater on crater on crater on ancient territory that's been there for over 4 billion years, unchanged. And Lamont again, I love that lunar spider. And Cassini crater, very unique. You don't see any craters on the moon looking like that. It's filled in with lava from within. That's additional impacts inside of it altered its interior. The Aristillus and Autolycus craters here. And right about here is where the first spaceship from Earth landed in 1959. The Russian Luna 2 struck the moon there. He said, okay, Earth people are on their way. Get ready. And Theophilus and Cyrillus, Catharina craters near Mare Nectaris. This is kind of an interesting study in how lunar craters age. Catharina formed first, and then Cyrillus impacted and showered the interior of Catharina with material and degraded it. And then along comes Theophilus and ruins both of them, throwing more material into it and degrading and ruining the crater even more. Yeah, Mare Humorum, highlighted by Gassendi crater, one of the most fascinating four-fractured craters. Like I said, it looks like an oatmeal cookie. All the fractures and cracks in it. And the always popular Cirrips, always popular, I'll get back there, there we go, Serpentine Ridge. And Mare Nectaris again. Tycho crater. And Clavius, one of the largest craters on the near side of the moon. And here's that strange elongated cigar-shaped Schiller again. If you can tell me how it was created, you might get your name mentioned in a research paper. Mare Crisium, very smooth, filled in with lava, giant impact crater. This feature up here, Lacus Mortis, which is Latin for Lake of Death. It's fascinating to me. It's an ancient impact crater that filled in with lava and then was struck right in the center by another crater. So it kind of created a bullseye effect. And Copernicus right after sunrise. And the crescent moon. We see it over in the western, or the western sky just above sunrise. And Mare Crisium, the first large mare that we see, emerges as the phase of the moon gets bigger and bigger. Kind of looks like a big unwinking eye staring at the Earth. So, To wrap it up, let me just say the moon is not just a graveyard for dead philosophers and scientists. You know, all the known craters on the moon are named after famous scientists and philosophers, but the moon is actually a dynamic world filled with wonders and scientific delights. If you know what you're looking for on the moon, recognize what created these features on the moon comes alive. It has a personality. You understand it. It's not just a place with bumps and dents and holes in it. You understand how the moon came into being, what formed its features, and how they came into being, how they relate to each other. So I hope I've been able to enlighten you a little bit, make the moon a slightly more interesting place. When you look at it through a telescope and you see a feature, oh, I know how that happened. That was formed because of volcanism, or this was an effect of the impact that created the big basins on the moon. And we're looking at mountains that were created by a giant impact and not like what happens on Earth. So the key thing about the moon, good thing about the moon is it's available for viewing almost every month. The moon does not care about light pollution or bright skies, bright lights. The moon is literally a backyard object. You don't need to go out into the country for dark skies. And it's the only celestial object we can observe with 1 kilometer resolution through our own backyard telescopes. So there is a lot to love about the moon. And I've been fascinated with the moon for 60 years, and I hope you will appreciate it a little bit more next time you look at the moon. So thank you for your attention.
So thank you, Robert. Thank you for sharing with us many of the very beautiful photos of the moon. If I were new to this field, I would probably ask whether all the pictures are really taken on Earth or whether it's taken by the spacecraft. And of course, I know today, on Earth you can really take these kind of really beautiful images. You can see the craters, see the mountains, really beautiful, without using a huge telescope, right? You can take it. But what you need is experience, you need patience, you need skills, you need a lot of time. And but we can really take all these beautiful images. Thank you, Robert. And any questions from the audience? In fact, Robert today he shared with us many of the photos, but he didn't tell me a lot about how he took these photos, what kind of equipment involved in taking all these photos. So, if you, audience, if you have any questions, you can feel free to ask.
Robert, thank you very much for your beautiful pictures for the images. I'm trying to image the moon as well using my 12.5-inch Dostonium. The thing is, I can guess that when you're taking the pictures, the seeing must be very good. So
it
that
helps.
it's very clean images.
Yeah, it
so
helps.
what time of the night at your time that you take the images? I guess that it may be something after midnight may be better.
No, actually, in
How many frames do you take for each image?
Yeah, in Texas, it's not late at night where it gets good. Traditionally, it clouds up late at night where I'm at. For a brief period of time after sundown, just as it's dark enough after dusk, for a brief period, it calms down a little bit. And I get about a half-hour window. And then I can see the sky getting shakier, and the seeing goes bad. So I try and do as much as I can immediately after sundown. Sometimes it's still twilight. So bright enough that I can still read. But later on, the seeing gets bad in my area. So I have to do it fairly quickly after sundown. To do the imaging, I typically take 5,000 frames. And my camera does 50 frames per second, so that doesn't take very long, less than 2 minutes. I take 5,000 frames. I use a freeware program called AutoStacker to automatically select the best 500 frames and stack them into one single image. And then I import that into Photoshop and then work with it in Photoshop. So it's not a hard process. It's a series of steps. Each one is fairly simple in its own right, but it takes time. The telescope must be accommodated, the telescope must be well focused, The seeing has to be good, the optics have to be clean, a lot of things have to go right. And the stacking process with AutoStacker takes time too. The original video is something like 11.5 gigabytes, and it gets reduced down into a single TIFF image. So it takes a lot of computational power to grind through that. You can start the process. What I do is, after I do my lunar imaging, I will start the process to work automatically overnight. It takes several hours to do it. So while I'm sleeping, it's reducing all of the data, and then I have all of my images in the morning. To process each single image in Photoshop, if I haven't spent at least a half an hour per image cleaning up all the artifacts, smoothing out the tones and fixing the dark areas, the shadows of the moon, getting rid of all the artifacts. If I haven't spent at least a half an hour on it, I haven't done it good enough. It takes time. And again, working with Photoshop is not that hard because we're only using just several commands in Photoshop. It's not a complex process. People think Photoshop is so horribly complex. Yes, Photoshop can do amazing things. It can probably do 1,000 things I've never even heard of, but I only use very few tools in Photoshop, but they're very essential for good lunar photography. And it just takes time to grind through it and do all the process. But none of it is complex. It just takes time. Sir?
My question is, there was a total lunar eclipse in United States,
Yeah.
and somebody or they recorded on the video, and they saw a flashlight
Yeah.
on the surface of the moon.
The lunar impact.
Can it prove that there should be many asteroids hitting the surface of the moon and create many new craters?
Yes.
And if somebody find a new crater, can he put his name on it, just like somebody find a new comet?
Well, there's a difference between naming a lunar crater and naming an asteroid or a comet that you discover. There are rules for naming features on the moon. Specific features have to be named after specific types of people, a particular type of science. Like I said, the lunar wrinkle ridges, named after Earth scientists. Craters can be named after famous scientists or philosophers. They cannot be named after military figures. But the main thing is, for a lunar feature to be named after you, you have to be dead for 3 years. So that kind of rules out crater Robert Reeves. So yeah, there's rules for naming things on the moon. If I saw a lunar impact like during the eclipse and tried to name it, it wouldn't work.
My other question is, it's very difficult to see the backside of the moon. And what is your opinion about China landing a spacecraft on the backside of the moon? Because I think the only way to see the backside of the moon is during a total solar eclipse, where your camera can photograph, the crater on the backside of the moon, if the exposure is good enough.
The moon is always facing away from us. So the only way we actually see the backside of the moon is by flying a spaceship on the backside and imaging it that way. From Earth, we will never see the backside of the moon, not even during a solar eclipse. But my opinion of China landing on the backside of the moon, I was very excited. I was very happy. The moon is for everybody. The moon is a place to be explored. The moon is a place to be used for the betterment of mankind. If we're smart enough to get there, I hope we're smart enough to use it correctly. Use it for science, use it for betterment of mankind, use it for resources if we have to in the future. But I'm very excited that China has joined the nations that have been to the moon. For so long, the moon was considered the domain of the space race between the Russians and the Americans. Not so anymore. It's a scientific playground for everybody. And I'm very excited that China has a very dynamic lunar program. And I'm looking forward to the next one that will bring back a sample of the moon from an area that neither the Apollo or the Russians have gone to. I'm very much looking forward to it.
Good.
So any other questions? Back.
My question is, the gravity of the moon affects the tides of Earth. Is the reverse true? Can the Earth's gravity affect the geological phenomenon on the moon?
Yes, it does. There's evidence from the instruments left on the moon by the Apollo missions. They placed seismometers on the moon, and there is a definite correlation between tides created by the Earth and lunar seismic activity. So it works both ways. The moon doesn't just tug on the Earth tugs on the moon as well. So it works both ways, yes. There's no liquid water on the moon to create tides like there is on Earth. But on the other hand, the moon also creates tides on the land. The Earth, the ground, heaves up toward the moon several inches as the moon passes over. It's not just the water that moves in the tides, but the oceans, the land will move also. And the same thing happens on the moon. So it does create seismic activity.
Other questions? Okay.
Robert, I'm curious, is your photos ever clean enough to find the lunar spacecraft on the moon?
I wish they would. No, the lunar spacecraft, the largest one, of course, is the Apollo landers, where they've got the 4 footpads that are about 10 meters apart. It seems like a large target, but our atmosphere and the limitations of optics keeps us down to just a little less than a half a kilometer resolution on the Earth. And of course, there are modern telescopes now that have adaptive optics, and they can correct for the distortion in the atmosphere. Are any of you familiar with Yuri Beletsky? I think he was speaking here in Hong Kong not too long ago, or did he not come to Hong Kong? Anyway, Yuri works with the observatories in Chile, the large observatories, and he did a program where he visually observed the moon with an 8-meter telescope with adaptive optics, specifically to try to see lunar landers at sunrise. It would be the best time to see them when they're casting real long shadows, and he searched and could not see them. So the only way we can see the lunar spacecraft on the surface of the moon is through photographs by the Lunar Reconnaissance Orbiter, and it has found all of them, except for the early Luna 9 and Luna 13, because they're too small. They're about the size of a beach ball. But all the others, the Russian landers, the Apollo landers, the Chinese landers, they've all been photographed and seen. So they're there.
Any other questions? I have a questions.
Sure.
Well, I'm going to ask if you were a teacher or an educator, that you're going to do a project with a student about taking a photo of the moon. What kind of project that you can suggest that involve like science, like measurement, like photography, that for a secondary school student or a team of students can do?
One thing that I wanted to get started in the United States, but life kind of got in the way and I couldn't complete it. But I wanted to work with the Education Foundation in North Texas to search for lunar meteorite impacts by observing the shadow side of the moon. Not the far side of the moon, but the shadow side. And very much like they saw that impact during the lunar eclipse, that happens a lot on the moon, actually. And we need to study the amount of the frequency of it. Not only from the standpoint that we're going to go back to the moon someday, and we need to know how big of a roof to put over our head, because things fall from the sky. It correlates to how often do these things also strike the Earth. Because as we saw in Russia several years ago, the Chelyabinsk meteorite, that thing could have been terrible. They were very lucky that nobody was killed. So we need to understand the rate of impacts, because Earth is as big a target as the moon. But we are going to go back to the moon someday, and we need to understand what the dangers are, characterize the rate of impacts, so we know what kind of shelters and so forth to make. But that would be something a student project could easily do with, say, a Celestron 11 telescope, a modest telescope, and a off-the-shelf ZWO or QHY camera, where you're looking at not the bright side of the moon, but the shadow side, and just continuously monitoring, looking for the flashes. And the brightness of the flash, of course, is related to how large the object is. So that's something students can easily do.
Thank you. So, any other questions?
I have a question.
All right.
Sure.
It may be our topic, but I cannot.
It may be our topic is related to the moon. We go to the moon by rocket. It's a very large rocket. At the last, when we arrive at the moon, we only have a little mass only remain on the moon. So if we want to go back from the moon to us, the step may be the same, but only the gravity will be smaller. So the rocket will be smaller or loaded. But I don't think that such small thing can come back to home. So why no people ask this question? It may be our topic, but it's related to the moon. Okay? Nobody can. I cannot search from the internet, and nobody, but no people raise this question. Okay? Could you have your anything of this?
I'm sorry, I didn't quite understand the question.
Actually, Louis Armstrong returned to Earth safe.
即係我講中文啦，或者俾我即係我哋咁難去，我哋咁大支火箭去到個月球啦。咁月球翻嚟都雖然可能支火箭可以細啲，但係都未至於細到而家我哋見到嗰個咁細咯。其實咁你可唔可以多講翻英文咧 ？OK。係咁個問題係
就咁細嘅嘢點翻到嚟地球咧？即係咁呢一個問題。May I try to translate?
Please.
Okay. It took such a large rocket, a huge rocket, to take up astronauts to the moon, to land on the moon, like Louis Armstrong. How could we bring them back without a huge rocket?
All right. Okay.
Oh, the rocket that took off from Earth, the Saturn V, huge rocket. It had to transport the entire spaceship to the moon to overcome Earth's gravity. Earth's gravity is 6 times what the moon's is. The lunar lander on the moon, much less gravity. It could be a smaller rocket. It just needs to escape the Earth. You need 7 miles per second velocity to leave Earth, go to the moon. To leave the moon, come back to Earth, you only need 2.4 kilometers per second, much less. So a smaller rocket can leave the moon and come back to Earth, but it takes a huge rocket to transport the entire spaceship to the moon. It has to be a large enough spaceship on the moon to come back to Earth. So it takes a very large rocket to put the smaller rocket on the moon. So the smaller rocket can come back to Earth with much less gravity. It doesn't take as much energy to leave the moon as it does to leave the Earth. It worked out real well. Neil Armstrong came home.
Robert,
it seems that the photo of moon is not taken by you.
Well, you caught me there. Not every picture was taken by. The last slide is not mine.
No, this is taken by satellite. You see the
Oh yeah, actually, I recognize the shape, the size, the way the moon is turned, so the Mare Crisium is facing us. That was actually taken by Apollo 10, by the Apollo 10 crew. Yeah, you're right. I said all these pictures were taken by me. The last slide, no. I'm sorry.
Maybe the last questions?
Okay.
One other question is your lunar photograph is incredible.
Thank you.
It's very high quality, you know. And the question is, what is the proper combination of the photo setup? What is the focal length of a telescope and the size of the